In this video, we'll go over the answer key for Wednesday, April 15th. And what we're looking at now is transport through the membrane. Remember, the membrane, polar head, nonpolar tails, so charged molecules can't go through it without help. Here, we're looking at a model of active transport by the sodium-potassium ATPase. Now, when I say ATPase, that means we need ATP to do transport. Here is a diagram what's happening, and you can notice, well, let me just say that this drawing is a little weird in that it kind of looks like the enzyme is moving, but really you just want to picture one enzyme in the membrane. And E1 and E2 are just different conformations of the enzyme. So what's happening is that one conformation, the E1, has ATP. It will bind a sodium inside the cell. Then, with the help of magnesium, it will hydrolyze that ATP, leave a phosphate on itself, be in a very high energy state, and transport the Na outside the cell. There on the outside, you're in a different conformation, E2, you still have the phosphate, you'll pick up some potassium, then you'll lose the phosphate, and once you lose the phosphate, you're going to go back to the E1 and deliver your potassium and get ATP again. So our first question is just having us thinking about a pump versus a transporter, which one is faster and why. That would be the pump. Pump is a continuous stream of ions, while the transporter will need a conformational change, and that takes time to do. Next is thinking about the sodium-potassium pump. So you're studying a drug, Albane, I think that's how you pronounce it, and it's poison that was used in warfare. So we know that Albane inhibits the sodium-potassium ATPase, and let's say you were doing experiments to try and determine how this poison worked. So your first experiment is that you add a solution with cells, and when you do that, you inhibit the movement of ions across the plasma membrane. However, if you inject this poison into the cells, nothing happens. What does that tell you about how this poison works? Well, that experiment tells you that it's only interacting with the part of the transporter that's on the outside of the cell, and it doesn't interact with the transporter that's on the inside of the cell. And part B, your next experiment is you add this poison to a solution of intact cells and allow full inhibition. You take the proteins and you do the crystal structure, and you also see that it's bound to the phosphate version. What does that tell you? Well, I do suggest you look at 3A, 3Y. So the way to do that is go to, just type in the Google PDB databank, and then at the very top when you get to that website, in the search part, type in 3A, 3Y. You'll see this poison interacting with this molecule, and you can start to understand how this poison works if you look at the molecule and look at the protein together. But just from this information without looking at the protein, we know that since we are only interacting with the phosphorylated form, we're interacting during the transition phase. That is, it's probably E1 phosphate. That is the form of the enzyme that this poison inhibits. All right, so we have another type of active transform. This is the potassium ATPase. It's a similar idea as we just talked about, E1, E2, ATP, calcium this time. And so we bring the calcium in, lose the phosphate, bring up hydrogen, and pump hydrogen out. So it's more or less the same idea as the sodium-potassium pump. We're just looking at a different system, calcium now. So here, question 3, we're asking another question about pumps. So the cells inside your wall will pump out HCl at a concentration of 0.15 molar. These protons are pumped out by a hydrogen potassium antiport, and a potassium chlorine symport is required as well. First off, what's the pH? So this is just, do you remember what pH means? Remember, P means minus log, so it's the minus log H concentration. So it's minus log 0.15, which is 0.182. Then, the second part of the question is, do you understand what these words mean? So first, antiporter. So I'm pumping hydrogen out, so that's going outside my cell. This box is my cell. If it's an antiporter, that means I must be pumping the potassium in. Now my other process is a symport, so potassium must be going out with chlorine as well. Now, let's think how this works. There's a lot of hydrogen out here. It's very acidic. So when I'm pumping hydrogen out, that is not favorable. So it must be favorable to pump potassium in. So I have to keep the concentration of potassium in my cell low. So how does this work then? Well, I'm pumping the potassium out to keep the inside of the cell low, so this part of the system works. Now I can couple that with pumping out chlorine, because if this is very acidic, that means there's a lot of positive charges. Chlorine is negative, so it would be favorable energetically to pump chlorine outside the cell, and so I'm taking this potassium more or less for free so I can keep the inside potassium concentration low. Right. Our next transporter is called the ABC transporter, and ABC stands for ATP binding cassette. That means these NBDs are nucleotide binding domains, and this works by binding ATP and then pumping out some kind of molecule. So cancer drugs that are resilient, they have a lot of these, and they just pump out whatever drugs you try to give them. So this question is, do you know what ABC stands for? What do they all have in common? ATP binding cassette. That is why they're called ABC transporters. Now, one type of ABC transporter that is associated with a disease, and the disease is cystic fibrosis, and that's CFTR. If you don't have working CFTR, you have cystic fibrosis. Basically, chlorines flow out of the cell because you have exactly one amino acid that's been deleted. Now, once that's deleted, you can't really flow chlorine out anymore because chlorine flow out of the cell with a working CFTR. Since you're not getting chlorine out, you're going to get a thickening of the mucus. You can get some bacteria in there and just a clogging of your airways. Next type of transport is the glucose transport in intestinal tissues. So you have a sodium potassium ATPase. Here we're using that energy to transport glucose. So let's see how this works. So here's our image. So we're bringing glucose and sodium in. Now glucose is then pumped out. But you can see for this glucose, we never use energy. Well, the energy is actually coming in this other transport. So bringing sodium inside the cell is energetically free with the glucose. But to make sure this stays low sodium, we need to pump the sodium out. So that's where this ATPase is coming in, where we pump the sodium back out and we can bring a potassium in. So what's actually interesting is that if you have water loss, so severe sale, I actually don't know what I meant to put there, but if you are going through diarrhea, you should really have glucose salt in water because that actually helps you uptake fluids a lot faster. So water reabsorption goes a lot faster if you have glucose salt in water, and it's mainly due to this system where I'm bringing glucose and sodium in at the same time. Glucose goes to my capillaries to make this energetically free, quote unquote. I need to spend energy somewhere. That's where the sodium potassium ATPase comes in. All right, another transporter, lactose permease, is a co-transporter, but if we look at this image, it looks a lot like what we've seen already. So it has two different forms, E2 and E1. Here we're doing lactose and hydrogen as well. And then we have the proton pump, which we're using to do oxidative phosphorylation here. So here we're getting lactose brought in through another one of our enzymes, and this is what it looks like here. And so you can think of these two different conformations as conformation 1, open to the cytoplasm. Conformation 2, just imagine this top closes off and this bottom opens up, and now you're open to the periplasm. All right, question 5, going back to just a review of these anti-transporters. So let's say you have a sodium hydrogen anti-transporter that's secondary active transport. So you excrete excess sodium from the cell. That is, outside the cell has higher sodium concentration than inside the cell. Therefore, is pH higher or lower than the intracellular pH? All right, so let's think about this. Sodium's leaving the cell, and we're going from an area of low concentration inside the cell to an area of high concentration outside the cell. That's favorable, unfavorable, and we need an input of energy to do that. However, we're doing secondary active transport, so we're not paying the price right here. We're paying the price somewhere else. So how do we pump this sodium out then? Well, that must mean that bringing the hydrogen in, since it's an anti-transporter, remember, antiport means sodium goes one direction, hydrogen goes the other. That must mean that bringing hydrogen in is energetically favorable. So if bringing in hydrogen is energetically favorable, that means there's a lower concentration of hydrogen inside the cell than outside the cell. That must mean that the extracellular pH is lower than the intracellular pH, because remember, lower pH means more hydrogens. And that's how this antiporter can work. With that, that's the end of these problems. I will see you in the next video.